The next 3 lectures focus on color, a fascinating subject. First, we'll look at some definitions and notions surrounding color theory, then at how color functions in nature, and we'll analyze a number of artist paintings and drawings to see how they actually use color. And you'll have the opportunity to apply what you learn in a range of exercises and drawing projects. I'd suggest using pastels, the chalky kind, not the oily ones. They're more versatile. Chalk pastels are made from pigments ground into a powder and held together with a water-based binder. They're relatively easy to use, especially if you've worked with charcoal. Pastels run from soft and powdery to hard and brittle. Rembrandt, Art Spectrum's, Schminke, and Sennelier are on the soft side, Prismacolor NuPastel, Cretacolor, Holbein, and Richardson on the hard side. Some people prefer one type to the other. Many artists use both. The soft pastels spread and blend more easily. The hard pastels can be sharpened to a point with a knife or razor blade for more precise work. Some manufacturers make pastel pencils that can also be used for more detailed work. You can purchase pastels both individually and in sets. If you purchase pastels individually, I'd suggest 14 to get started: a green, a blue violet, a red, an orange, and a yellow, and 4 earth colors: a yellow earth like a yellow ochre, an orange earth like a raw sienna, and a red earth like a burnt sienna. I'd also suggest getting a darker, less saturated brown like a Van Dyke brown or a burnt umber, and a white, black, and gray. Many manufacturers make light to dark gradations of their colors. They number them. The darkest version usually gets the lowest number, the purest grade gets a middle number, and the lightest gets the highest number. A good way to expand on the basic group is to get 3 of each color when available. For example, choose a green and get 3 versions: the darkest, the purest, and the lightest. A further way to build on a set is to get 3 different greens, or blues, or reds, ones that have different qualities, like a center iconic blue, another more toward the green, and another more toward the violet. And you could also expand by buying both softs and hards of similar colors. Now, you can also purchase a set. If you go this route, look at the range of colors to see what bases are covered in light of what I just suggested regarding individual sticks. As with most of the materials we've discussed, there's no standardization between manufacturers. 2 ultramarine blues made by 2 different manufacturers may well be different. And there are a wide variety of names, some particular to a single manufacturer. So it's a good idea to look at the sticks and not just depend on the names until you know the brand. Pastel, like graphite and charcoal, can be hatched, blended, layered, and manipulated in myriad ways. Pastel papers tend to have a fair amount of tooth, and that serves to abrade the chalk and hold it on the surface. As you may remember from high school physics, Isaac Newton passed white light through a prism and observed it split apart into bands of color. This is an illustration from his 1704 book, Optics. He described the spectrum he saw as consisting of 7 colors: red, orange, yellow, green, blue, indigo, and violet. The number of colors, 7, derived from his belief that the color spectrum had an underlying connection with the 7-note musical scale and the number of the days in the week, among other things. He arranged the colors in a circle, the first color wheel. The letters at the ends of the spokes along the circle's circumference show the musical note in scale order he associated with a given color. Physics tells us that color is determined by the distance between waves or wavelengths of a given wave of light. This is referred to as wave quality. Red has the widest wavelength, and as we progress around Newton's circle, wavelengths get narrower. An object or substance appears to be a certain color because it's reflecting those waves and absorbing all the others. The green block looks green because it absorbs all other wave qualities and reflects the green ones back to us. Similarly, the yellow reflects the yellow, and the red, the red. All else being equal, the lightness or darkness of an object or substance is determined by the quantity of light waves it reflects or absorbs. White objects, like the white paper we draw on, reflect most of the light waves coming at them. Black substances, like the ink we use, absorb most of the light waves coming at them. That's related to what we experience with a white or silver car being cooler than a black one in summer heat. And this was actually tested at the Lawrence Berkeley National Laboratory in 2011. They found the cabin air temperature of a white or silver car to be 9 to 11 degrees lower on average than an identical black one. In any case, here the yellow block reflects more light than green or red, so the yellow appears lighter. Newton also showed that he could take his bands of colored light, pass them back through a prism, and get white light. Pigments behave differently. Take 7 different pastels, same as his colors, mix them together, you get a darkish mud. That said, the color wheel is still very much with us today, though we've adapted it to our own purposes. And this has to do with how pigments, as opposed to light, are mixed and how colors relate. For artists, the most basic group of colors consists of a triad, red, yellow, and blue, referred to as primary colors. They're primaries because you can't make them by mixing other pigments. The next 3 colors, the secondaries, are made by mixing the primaries. Yellow and blue produce green, blue and red, violet, red and yellow, orange. Taken together, this yields a color wheel of 3 primaries and 3 secondaries. To get familiar with all this, I'd suggest drawing along with what we'll be discussing. Here you could lay your primaries and mix secondaries or make a primary-secondary color wheel. If we mix intermediary steps between any of the 6 primaries and secondaries, we get 6 new colors referred to as tertiaries. These include yellow-green, green-blue, blue-violet, violet-red, red-orange, and orange-yellow. You could mix these too. And we could mix each of these 12 colors with its neighbor to create another 12 hues. One of the things you'll note is that as we add more transitional colors, the visual path around the wheel is smoother, more legato, less staccato. For our purposes, a 6-color wheel will do fine to help us understand the basic relationships among the colors. But these same relationships would apply to a 12-hue, 24-hue, or 48-hue wheel. We think of colors as having temperature. You likely note that yellow, orange, and red form a group. These are the warm colors. Green, blue, and violet are the cools. With yellow at the 12 o'clock position, the color wheel reveals the warm colors dividing from the cools, from the top right to lower left along a diagonal. One side feels like day, the other like night. One like sunshine and warmth, the other like a cool stream in a dark forest. They represent different temperatures and different moods. With yellow at the 12 o'clock position, our color wheels reveal the hues organized from top to bottom, light to dark. As we noted, with fewer transitional colors, the visual path's choppier. More transitional colors, smoother. That's because transitional colors share elements of the hues on either side. Red and orange both contain red, so they feel similar. Same with blue and violet, they share blue. And both are smoother transitions than, say, yellow to red or yellow to blue. These feel like big jumps because these colors have nothing in common. In the 6-color wheel, we glide through orange to get to red, glide through green to get to blue, smoother. So when we want smooth transitions, we use colors that share common elements. And colors that share common elements or qualities will appear to hang together and form a shape. When we want abrupt transitions and when we want an area to feel like an independent shape, we'll do the opposite. On the wheel of primaries and secondaries, the colors that are next to one another are called adjacent or analogous colors. Each color shares something with its neighbor. Like the warm and cool groups, there are other, more subtle groups. The 3 colors that share yellow form a group, yellow, orange, and green. Though it's worth pointing out that not all adjacent colors are equally similar. The temperature divides a significant one. A pure yellow will feel more similar to a pure orange than to a pure green. While yellow and green share yellow, green contains blue, a contrasting cool color. Yellow and orange share yellow, and neither contains anything cool, so they share warmth as well. Same thing with red, orange, and violet. Other significant groupings include the ones that contain 2 primaries and their secondary, 2 parents and their offspring. Yellow, blue, and green, blue, red, and violet, and red, yellow, and orange, already mentioned as the warm group. The opposite of analogous color is complementary color, also referred to as opposite color. That's because these pairs sit opposite one another on the wheel. That puts each one as far away as possible from its opposite. Our three complementary pairs are yellow and violet, orange and blue, and red and green. While analogous colors share a component color, complements have nothing in common. There's no yellow in violet and no violet or red or blue in yellow. There's no orange or red or yellow in blue and no blue in orange. There's no red in green and no green or yellow or blue in red. Nothing in common. We could say that analogous colors are like two grays. They have contrast. We can tell them apart, but they share elements. Each has some amount of black and some amount of white. There's something different, but something shared. We get some contrast. How much depends on how much is different and how much shared. On our value scale, a number 7 gray and a number 8 gray share a lot. Not a lot of contrast, not unlike blue and violet. On the other hand, a number 2 gray and a number 6 gray share much less, more contrast, not unlike yellow and green. But complementary colors are extreme. They're like black and white, no white and black, no black and white. No yellow and violet, no violet and yellow. Nothing in common, highest contrast. That said, the three pairs of complements have different personalities. The wheel's organized top to bottom, light to dark. So the yellow-violet pair has the greatest value contrast of the three pairs. Orange and blue follow. Most people find these more mellow, and red and green the most similar in value. In an early lecture, I noted that we think of each color as having three attributes: hue, value, and saturation. Hue coincides with the color's name. It's the yellow or green or blue character of the color. Value refers to the color's lightness or darkness. Any color can be made lighter or darker. A color made lighter by adding white's called a tint. One made darker by adding black, a shade. Some color wheels plot tints and shades radiating from each hue. White, black, and gray are referred to as neutrals. They're considered colorless. When added to other colors, they don't change the hue of that color, they change its value, making it lighter or darker. That's the theory. Doesn't always work that way. Mix black with yellow, you'll get a green, not a dark yellow. Even in the example here, the dark yellow has a greenish cast. There are also a number of ways of making things lighter or darker that don't depend on adding white or black. For instance, you can apply a color transparently. On a light ground, it will appear lighter, more opaquely to make it darker. Or apply it to a darker ground. The ground could be the paper or a color that's been spray fixed. And the decision to blend or not will also affect the color's apparent value. The third attribute of color is saturation. This refers to the color's level of purity. We can create versions of all our colors stretching from very gray at the achromatic end to the most intensely saturated at the other. Often, when we change the value of a color by adding white, black, or some other neutralizing color, we're also lowering the saturation. When analyzing a color, we want to understand it in relation to these three scales: hue, value, and saturation. Again, in theory, you can create all possible colors, all secondaries, tertiaries of every value and saturation using the three primaries in black and white. But it doesn't work that way with pigments. We'll come back to this later. The essential point here is to begin to be able to read hue in something that's somewhat neutral. Look at the more neutral versions of the color in these wheels. Can you still feel the underlying color? You may have heard it said that you get neutral gray by mixing complements. That's not quite true. The actual color you get will depend on several factors. There's the material. Pastel behaves one way, oil paint another. Then there's how you actually mix the colors. And there's a specific pigment. Not all blues are the same. Let's take a look at how this works. Here are three pairs of complements. Overlay yellow on violet, then violet on yellow. Two different colors. So order matters. But neither's a gray, though both are more neutral than yellow or violet alone. Same thing with blue and orange, or red and green. So far, I've mixed directly. But if I blend, I get a different color. And if I apply the color on the swab, it's more neutral. The colors have been more thoroughly mixed. The neutrality will be more pronounced if I use neutral versions of my complements to start with. Here, a more neutral blue and orange. We're entering into the world of chromatic grays, colorful grays, neutral versions of their parent colors, and I can make each one a little warmer or a little cooler. Adding white, a neutral will not only lighten, it will increase its neutrality, as will adding a neutral gray. This kind of color is extraordinarily useful because so many of the things around us are not saturated nameable color, and we often need to make subtle distinctions between things. If drawing with value is like playing checkers, drawing with color is like playing three-dimensional checkers. With value, an area can be either lighter or darker. So tonal value in and of itself offers us one kind of contrast. With color, we can have contrast happening along three scales simultaneously: hue, value, and saturation. If all three are the same, the color will be identical. We won't see any distinction between two shades. But if I vary one factor even a little bit, let's say keep the hue and saturation about the same, but lighten the value, I get contrast and differentiation. Or instead, I could keep the hue and value about the same and change the saturation. Or I could keep the value and saturation and change the hue. Or I could vary all three, hue, value, and saturation. That means a lot of contrast. With two shades and three variables, there are 8 possible scenarios. Hue, value, and saturation could all be the same, or all be different, or any two could be the same and one different, or any two could be different and one the same. But there are more than 8 possibilities, because the amount we could vary any of these factors could be anywhere from a little to a lot along a sliding scale. So the actual number of specific contrasts you could create with only 2 shades is nearly infinite, more than you could move through in a lifetime. There are a couple other types of contrast we need to consider. One we've already mentioned is warm to cool. Another's contrast of amount. All else being equal, the greater the amount of a given color, the more that color will feel dominant. In the first lecture on value, we learned that value is relative. White surrounded by black will appear brighter. Black surrounded by white, darker. We experience color similarly. A red surrounded by black appears brighter, surrounded by white, dimmer. Here we have an identical red in 3 different red grounds. Each time the central red appears to be a somewhat different color. In the brightest ground, it's the most muted. In the darkest, the brightest. As the ground gets darker and less saturated, the internal square appears to get lighter, more saturated, more orange. Not surprisingly, the red square is more saturated in a neutral ground. Here we have 4 different saturated ground colors. The first a red variant, the next a violet, a color containing red, then a blue, and finally red's complement, green. The red appears more saturated as the ground's hue moves from similar to complementary. The same blue-green appears greener in a blue and bluer in a green. The same violet appears redder in a blue and bluer in a red-violet. And a color that's pretty gray in a bluish ground's bluer in an orange one. You can make some color studies of your own along these lines. Many of these and related principles were outlined by Johannes Itten and his student and later colleague Joseph Albers. Both were professors of art in Germany at the Bauhaus. Albers would go on to teach at Yale. In 1963, he published one of the seminal 20th century works on color, aptly titled The Interaction of Color. Of course, artists have been aware of color's relative nature for some time. In 1885, Van Gogh wrote to his brother about his painting The Potato Eaters. He explained that it really needed to be hung on a golden-colored wall. He wrote, "It simply mustn't be seen without being set off in this way. It will not appear to full advantage against a dark background, and especially not against a dull background." Van Gogh understood that a painting on the wall is very similar to a rectangle of color inside another rectangle of color. In terms of drawing, this means it's smart to block in general color overall first, because the way color reads is contextual. Drawing one object, finishing it, and then going on to the next can result in real problems. The color that at first looked right could look all wrong as a budding color is added. The same situation as with value, but more so. We should note that color has had symbolic meaning. Some of this is local and culturally specific. Some associations are more widespread. Unsurprisingly, the warm colors red, orange, and yellow have been associated with heat, warmth, fire, and energy. Red particularly with heart, passion, and love, but also with blood, violence, and danger. Think stop sign. Green has associations with growth, life, and freshness, and in the US, money. Blue is often construed as calm, or embodying the coolness of water, and, as in the blues, sadness. White, at least in the West, has been associated with day, the Apollonian, reason, and calm, and also associated with purity, like brides in white. Black has associations with night, terror, and deaths, but also with elegance and romance. Think limo, tuxedo, and black party dress. Of course, a fair amount of this is a matter of local culture. Among the Chinese, white's associated with death, and red's a color of prosperity. Most of what we've just discussed would come under the heading color theory. But in order to use color in drawing, it helps to understand how we actually see color. When talking about objects like these blocks, we refer to their greenness, yellowness, or redness as their local color. When we look at most things, we're seeing many more colors than their local colors. In fact, here are 16 colors that are present in the image of the blocks. The 4 in the center are obvious, a red, a yellow, and 2 greens. But some of the others might seem more curious, and a number of these don't really have names. The reason why we have so many colors here is that local color is influenced by environmental factors. The first factor is light. The green block is receiving most light from above right, and we see 3 main colors associated with this. The top ridge of the block receives most light and is the lightest. The side plane gets the next largest amount of light, and it's a bit darker. The front plane receives the least light, it's darkest. But the color isn't only getting darker, it's also moving from the yellow to the blue. The light to dark shift is accompanied by a warm-cool shift. Why? Because the light itself is yellow. As Leonardo observed, il colore dello illuminato partecipa del colore dell'illuminante. The color of the object receiving light is affected by the color of the light source. We see similar progressions across the yellow and the red block's planes, though the right face of the yellow block's in the shadow of the red block, so it receives more light from above left. As you may have already noticed, there's a second factor affecting the color here, and that's reflectivity. Leonardo comments on this too. I colori degli oggetti illuminati si imprimono nelle superfici l'un dell'altro. The colors of objects receiving light reflect on the surfaces one to the other. For example, look at the bottom right edge of the green block. It goes in orange ochre or orange-green kind of color. That's because the reflection of the red block is mixing with the green local color on its surface. If we look at the shadow side of the yellow block, we see the same thing. The red block is reflecting onto the yellow surface to create a succession of earth tones that contain both yellow and red. As we move across the yellow plane, the color gets progressively darker and redder. Now you might ask, why isn't the yellow reflecting into the red? Well, it is, just not that much. To reflect color, a surface has to receive a sufficient amount of light. The right plane of the yellow is pretty much in shadow, so it reflects less. The blocks aren't only reflecting one onto the other, they're also reflecting down onto the white surface. The reflections of the lighter planes are lighter, the reflections of the shadow planes are darker. All the reflections are pretty neutral, but can you see color in the neutrals? Do you see how the reflection of the yellow cube is more yellow, the red more red? When thinking about reflective color, the other major factor is the surface concerned. A more highly reflective surface will, by definition, produce a more defined reflection. That means greater saturation and higher value contrast. There are a couple of other things worth pointing out here. Generally, the light tone or halftone will have greater saturation than the highlight or shadow side. The very lightness of the highlight subtracts from its saturation. And unless there's some very strong reflection into the shadow side, it'll appear less saturated. So while we name colors for convenience, that's green or red or yellow, what we actually see is a named color affected by the direction of the light, the amount of light a given surface receives, the color of the light, and any reflected color from other objects in the environment. Indoors, under incandescent light, illuminated planes go warmer and shadows generally cooler. Under fluorescent light, illuminated planes go cooler and the shadows can appear warmer. Had the blocks been lit with blue daylight through a window, the illuminated planes would go cooler. Moonlight through a window would be different again. At night, we'll often get strong contrasts of light and shadow and strong saturation in an artificially illuminated area. That's because dark is the default and light, like a street lamp or car's headlight, will illuminate some portion of the scene. And imagine those blocks at night sitting on a shelf in a half-dark closet. Well, without strong light, the saturations all diminish and the contrast of light and shadow are reduced. We may not even be able to tell the block's colors at all. In this example, the blocks were posed in a photographer's studio, indoors. But these same factors hold true when we move outdoors, and there are a couple others that come into play as well. In an earlier lecture, I discussed color and atmospheric or aerial perspective. We noticed that distance affects the way we perceive color. When things are closer, their colors appear to have greater value contrast and greater saturation. As they recede, less. One way of thinking about this is that the atmosphere, like the yellow bulb on the blocks, lends its color to what we see. And as things like hills and trees recede into space, they take on more and more of the color of the atmosphere itself. That's because with distance, there's more and more atmosphere between us and what we're seeing. Here, we get an admixture of light blue. Leonardo explains this. There is another kind of perspective which I call aerial perspective. In an atmosphere, the remotest objects seen through it, as mountains, in consequence of the great quantity of atmosphere between your eye and them, appear blue and almost of the same hue as the atmosphere itself. And when the sky is cool, the shadows of objects in the landscape tend to reflect that coolness. On the other hand, a sun-filled sky can tinge everything with golden tones. Other skies will suffuse a landscape in brown. A cloudy dusk can go indigo blue. An overcast day to violet grays, and winter cold to icy ones. Like the blocks, many surfaces in nature reflect color. Water, of course, would be an obvious example. But colors reflecting in nature more subtly all the time, just like in the colored blocks. In the lectures on value, we saw how we could create the illusion of light and volume with as few as 2 values, a light and a dark to stand for everything from highlight to form shadow to cast shadow. Or we could use 3, a light, a halftone, and a dark. Or 9, 1 each for the highlight, light, and halftone, then 2 steps for the form shadow, then a reflected light, a reflected shadow, a cast shadow, and light from the object reflected into the shadow. What's clear is that there's no right way, but different approaches will yield different results. The more or less on and off value of the Daumier has one feel, the more modulated approach in the Lundin another. With color, the number of possibilities for modulating form increases exponentially. In the next lecture, we'll take an in-depth look at how artists use color. For now, I'd like to look at some of the ways artists modulate form. In the woman's flesh, Vermeer modulates light to dark and simultaneously warm to cool, all in a fairly neutral complementary orange-blue range. Cézanne's values are much closer and his saturation much greater, but he also modulates warm to cool, here analogous yellow to green. Van Gogh also modulates warm-cool in the head, like Vermeer orange-blue, though much more saturated. And Wayne Thiebaud pumps the saturation and compounds this with high-value contrast. While Monet moves light to dark in the man's head, he stays within the warm, though the form shadow is more neutral. But in the woman's dress, the lights are cool and the form shadow goes warmer. And let's look at the woman's back in this William Merritt Chase pastel. The highlights are cool, the surrounding light warm. As we move into the form shadow, we go cooler, into the umbra warmer. In the next lecture, we'll learn more about how we can use and create form in just about any kind of palette.